Friends, so far we have studied the angle stability of power systems. In the previous lectures, we have studied the basic concepts of tangent stability, dynamic stability, modeling of the components and various techniques for analyzing the tangent stability and dynamic stability of a system. Today, we shall study another very important form of stability, that is called voltage stability of a power system. This subject has been the subject of concern over the last 2 decades, and over the last 2 decades a lot of research work has been conducted in the area of voltage stability, and the standard resource material for this subject is available in chapter 14 of this book, Power System Stability and Control, written by Prabha Kundur. This chapter 14 deals with the voltage stability of the power system. Then there is one more book which is exclusively written to deal with this subject, that is Power System Voltage Stability by Carson W. Taylor. This book is exclusively written and addresses this voltage stability problem. The resource material for my presentation is drawn mainly from these 2 resources, and we will study this voltage stability problem in somewhat detail in the coming lectures. The voltage stability problem we will actually examine by studying the following aspects of the subject. That is, we will examine the basic concepts of voltage stability, and while trying to understand the basic concepts, we will study the characteristics of the transmission lines, characteristic of the generators, load characteristics, which forms a very important aspect, that is the load characteristics affect the voltage stability to a large extent. Then we will study the characteristics of reactive compensating devices. The reactive compensating devices are shunt capacitors, regulated shunt compensation. When we talk about regulated shunt compensation, under this category comes the static var compensators and STATCOM. We will study the characteristic of series capacitors, and we will also study the effect of control series compensation, that is thyristor control series capacitors and the static synchronous series condenser. Then after studying the characteristic of these devices which affect the voltage stability, we will examine the voltage collapse phenomena, that is how the voltage collapse takes place in a power system. The next point which we will examine is the classification of voltage stability, that is the voltage stability problem is generally divided into 2 subcategories. One is called the tangent voltage stability problem, and it is called small signal voltage stability problem. It is also divided into the another 2 categories. One is called the static voltage stability problem, and another is the dynamic voltage stability problem. Therefore, this subject will be dealt in detail. Then for any given system, one should know how to analyze the stability. Therefore, we will examine the techniques which are available for analyzing the voltage stability of a system. Now, while analyzing, we will deal with the modeling requirements of the system. Then we will talk about the dynamic analysis, that is the static analysis. That is, as I told you, that we divide this stability problem, voltage stability problem, into 2 main categories, static stability and another is dynamic stability. Therefore, we will examine the static and dynamic stability analysis techniques. Then there is a concept of the determination of shortest distance to instability, that is when you are operating at a certain point, how far we are from the instability point, that is what called the shortest distance. Then we will just address the continuation power flow, which is used for analyzing the stability problem. Then at the end we will examine the techniques which can be used for prevention of voltage collapse. The various measures which can be used for avoiding the voltage collapse are put under major headings like system design measures. That is, when we design the system, we must take care of that the system is operated and so that we avoid the instability of the system. That is, right at the design stage we incorporate certain features so that the voltage instability problem does not take place. The various design measures are application of reactive power compensating devices, control or fixed, then control of network voltage and generator reactive power output, because generator becomes a very important source of reactive power. So, that we should know how to control, what techniques can be used to control the network voltage at various points and also the generator reactive power output. Then protection plays very significant role in the power system stability. Therefore, one has to incorporate certain features which have a coordination between the protection and control. When I talk about control, means control of generators, control of shunt and series compensating devices. Then we will also examine the control of voltage transformer tape changers. Then under voltage load shedding, for improving the tangent stability of the system, that is angle stability, we have some phenomena called the under frequency load shedding. Similarly, for avoiding the voltage instability phenomena, one can resort to under voltage load shedding. That is, when the voltage is less than a certain level, then you can shed some of the load or disconnect some of the loads. It is called under voltage load shedding. Now, these measures are basically the measures which are to be incorporated right at the design stage of the system. That is, when you design your system, you incorporate these features so that you can appropriately control the network and the voltage instability problem can be avoided. Then there are certain measures which can be adopted, that you operate the system, you maintain certain stability margin, that is a shortest distance to stability, that is you have to maintain that stability margin, you maintain certain spinning reserve, and there should be trained operators to take appropriate action in time, so that instability problem does not occur. Now, let us look into what is the basic definition of voltage stability. The voltage stability is concerned with the ability of a power system to maintain acceptable voltages at all buses in the system under normal conditions and after being subjected to disturbance. This is a very standard definition, that is, voltage stability is concerned with the ability of the power system to maintain acceptable voltages at all buses in the system under normal operating conditions and after being subjected to disturbance. Suppose some sort of disturbance occurs, like some generator dropping or some line dropping, right, or some fault occurring and fault being cleared, right. These are certain disturbances. Therefore, under normal operating condition as well as after the disturbance has occurred, under both these conditions the power system should have the ability to maintain acceptable voltage level. Then we say that this is the voltage stability of the system. That means again voltage stability is concerned with the ability of the power system to maintain acceptable voltages at all buses in the system under normal conditions and after being subjected to a disturbance. Now, a system enters a state of voltage instability, a system enters a state of voltage instability when a disturbance, the disturbance may be in the form of increase in load demand or change in system condition, causes a progressive and uncontrollable decline of voltage. That is suppose you have a system, right, and in that system suppose there is a increase in load or there is some sort of system change, there is a dropping line or some change in the system takes place, network topology, right. Then in case suppose this disturbance will cause a progressive and uncontrollable decline of voltage, then this type of situation is the voltage instability problem. That is, the voltage will decrease continuously and progressively, and we are not in a position to control and stop the decrease or halt the decrease. The main factors causing instability, the main factor causing instability is the inability of the power system to meet the demand of reactive power. This is again very important point. The crux of the whole problem is that the power system is not in a position to meet the reactive power demand. That any power system, as we talk about, the angle instability occurs because of unbalance between the generation and load. Similarly, here if there is a situation where the reactive power demanded from the network is not equal to the reactive power supplied by the network, that is, the power system is not in a position to meet the reactive power demand. That is the main problem. Now, here let me again mention that under what circumstances this problem occurs, because generally when a power system is operating, right, then in case a power system is heavily stressed in the sense that it is heavily loaded, right, then there is a possibility of voltage instability occurring. That is, the voltage stability problems normally occur in heavily stressed systems, while the disturbance leading to voltage collapse may be initiated by a variety of causes. The underlying problem is an inherent weakness of the power system. As I have told you, actually the one is that the power system is not in a position to meet the reactive power demand. Now, reactive power demand meeting is one of the most important requirement, but at the same time suppose the system is heavily loaded, right, and now you increase the load beyond a certain point, then system is not in a position to maintain the required reactive power and the voltage will decline and may continuously decline or continuously decrease, may not be controllable. In fact, actually in some systems the main cause of voltage instability used to be the long transmission lines, right, or if you have a well interconnected system and the system is loaded heavily, and if you put additional load, then the possibility of voltage collapse may occur. In fact, these two terms, voltage instability and voltage collapse, are used interchangeably. Many voltage collapse phenomena have occurred during the last 3 decades, and where some sort of disturbance occurs, and you will find actually that the voltage at most of the buses in the system will go below a certain acceptable level. It is called the voltage collapse phenomena, and it occurs actually in a very different type of manner. In the sense, you start you trigger some sort of disturbance, voltage drops, and then it continue to drop. We are not in a position to bring it back to the. If we are in a position to control the system after disturbance and bring back the voltage to the required level, then it becomes voltage stability, not the voltage instability problem, right. Therefore, to maintain the system voltage stable, we have to have fast reactive power controls in the system. Now, let me just sum up what are the basic factors which contributes to voltage collapse. Basic factors which contribute to voltage collapse are the strength of transmission network and power transfer level. When I talk about the strength of the power transmission network, in the sense that when the transmission network is short and it has a high power transfer capability, right, then we say that the power transmission network is strong, its inherent reactance is low. And if this power transmission network may be strong and it may be supplying huge amount of power, so that it may be operating near the limiting condition. Therefore, one of the reason is the strength of the transmission network and the power transfer level at which you are operating. Then the next important component is the generator reactive power or voltage control limits. A synchronous generator is to be always operated such that its certain parameters are within the limits. For example, the armature current should be within the limits, the field current should be within the limits, and therefore, the operating condition or under how the power generator is to be operated is always determined by the operating chart. There is a operating chart of the generator, right. So, that within that chart one has to always operate, right. In case you are operating such that if you are supplying the maximum reactive power output, then there is no scope for further increasing the reactive power output. I shall discuss this generator reactive power voltage control limits. These aspects we will discuss in detail later on. Then comes the load characteristics. Most of the loads which we come across are voltage dependent, that is, the loads are voltage and frequency dependent, and as the system voltage increases, the real power and the reactive power absorbed by the load varies, right. And therefore, how the real and reactive power absorbed by the load varies affects the voltage collapse phenomena. Right? The load characteristics, the load characteristics, sometimes we have constant power loads, so that even the voltage is fluctuating, the P and Q does not change. There may be constant impedance loads where the power consumed is proportional to V square, right. There may be constant current loads, right. Therefore, we have normally the composite load where part of the load is constant impedance load, part of the load is constant power load, part of the load is constant current load, and therefore, the load characteristics affect the voltage collapse phenomena to a very large extent. As I already mentioned, the characteristic of the reactive compensation devices, as I told you, the reactive compensating devices are basically synchronous condenser, the fixed capacitors, switch capacitors, and continuously controlled devices like SVC, STATCOM, then other series devices like TCSC, triple SC and so on. That the characteristic of these devices also affect a lot. Then one of the very important device which affects the voltage stability is the action of underload tap changer of the transformers. In any power system we have the underload tap changers, we call ULTC, or sometimes we call the on load tap changers, and the function of this on load tap changer is to maintain the voltage at the load terminals. And many times it is seen, depending upon the load characteristic the ULTC may help in improving the stability, or sometimes it acts in a adverse way. We will discuss this effect of ULTC on voltage collapse phenomena separately. Now, to understand some of the basic features of or certain basic concepts of voltage instability or voltage stability, we consider a very simple network Let us say there is a voltage source E s connected to a load whose impedance is ZLD angle phi, and this load is supplied through a transmission line whose impedance is denoted as ZLN angle theta. This is the impedance of the transmission line network or transmission line. This is the impedance of the source, or you can even look actually that this is the Thevenin equivalent of the network looking into the two terminals at which the load is connected. When in that case E s becomes the Thevenin voltage and ZLN becomes the Thevenin impedance. We will denote the power consumed or the complex power consumed by this load as P r plus J times Q r. Now, we will first derive the expression for the received voltage V r in terms of the various parameters of the network. The current I which flows in this network, I will denote the current I call this I bar, right. This current I bar is written as the voltage divided by sum of the two impedances, the line impedance plus the load impedance, right, where we denote the line impedance as ZLN angle theta or in the complex form ZLN bar. Similarly, the load impedance we will denote as ZLD bar as ZLD angle phi, and this voltage E s will be taken as reference, that is E s angle 0 degrees. The expression for the magnitude of current, now here this is the expression for magnitude of current, can be written in terms of the source voltage E s and the parameters of the line and load impedance, that is ZLN cos phi plus ZLD cos this is cos theta cos phi whole square plus ZLN sin theta plus ZLD sin phi whole square. This can be derived by substituting the expression for ZLN, ZLD, and then you can write down the expression for the magnitude of the current. Okay. Now, this expression for this current can be written as 1 by square root of f into E s by ZLN, where f is defined as f is 1 plus ZLD by ZLN whole square plus 2 times ZLD by ZLN cos of theta minus phi. Now, the voltage at the load end, that is the receiving end voltage V r, the magnitude only can be written as the magnitude of the load impedance multiplied by magnitude of current, ZLD into I. This is writing only the magnitude, which can be written as 1 by square root of f ZLD by ZLN into S. That is, you substitute here the expression for I, right, you will get the expression for voltage at the load end in this form, and the power received by the load, the real power received by the load is V r into I cos phi, where V r is the voltage across the load, I is the current, and since I have considered actually the phase angle of the load impedance as phi, so that the received power is written as V r into I into cos phi. Okay. Or the P r can be written in terms of the other parameters like load impedance and this expression f, this f E s upon ZLN whole square into cos phi. In fact, to understand the behavior of this simple network, what we are interested is, we want to know that how these two important parameters, one is the voltage across the load and the power which is derived by the load, drawn by the load, right, are affected by the impedance and other parameters of the network. See, after deriving the expression for receiving end voltage and the power received by the load, we plot the variation of the receiving end voltage and receiving end power in terms of a normalized impedance, that is we use actually this quantity ZLD upon ZLN on the x axis, that is the normalized impedance, and then plot the variation of the receiving end voltage VR, and we plot the variation of the receiving end power PR and the current I. Now, these three quantities, that is current I and the power and this voltage, they are again plotted as normalized quantities. That is the receiving end voltage VR. This graph shows, this blue graph shows the variation of receiving end voltage with the variation of ZLD by ZLN. Therefore, this receiving end voltage is shown as VR divided by ES. That is, what is plotted is the value of receiving voltage in per unit, considering the system voltage ES as 1 per unit or the base quantity. Therefore, you can easily see here that as the impedance ZLD, that is the impedance of the load increases, the receiving end voltage decreases continuously. Now, the receiving end power is concerned, receiving end power is plotted as a ratio of the actual power PR divided by PR max, that is the maximum power what is plotted here is PR divided by PR max, that is the maximum power. And you can see here actually that this graph shows the variation of this quantity PR upon PR max. That is, when this power received becomes maximum, then this ratio is equal to 1. Therefore, this quantity is 1 here. This is the maximum power which is received. That is what we see here is that as the magnitude of this impedance ZLD increases, the receiving end power first increases at a fast rate and then attains a maximum value, then it starts decreasing, right. Now, we can see here actually that this is the maximum power which is received by the load, and for power to be received maximum power, the ratio of ZLD to ZLN is 1. That is, when the magnitude of load impedance is equal to the magnitude of the source impedance, right, then the power transfer to the load becomes maximum. This is the maximum power transfer theorem also. That is, if you have actually a source whose internal impedance is equal to ZLN and supplying power to a load whose impedance is ZLD, then the condition for maximum power transfer is that these two impedances should be equal in magnitude, right. Therefore, this is what is happening here. When this ratio is equal to 1, the power transfer is maximum. Now, generally the operating condition is on this region of this curve, on this portion of the curve, that the power increases when the load impedance is increased, right. Now, when we see that from this point onwards, when we increase the load impedance, the power decreases, right. Therefore, now suppose when you come actually at any of these points, let us see this point, in case the load is offering a constant impedance load, if the impedance of the load is constant, then this is also a stable operating point. That is, you can operate anywhere on this curve, right, in case the load is a stable load is a constant impedance load. The another characteristic of interest generally is that we plot the PR versus VR, that is, we plot actually the receiving end voltage versus the real power, rather than plotting the expression in terms of the load impedance, we plot the receiving end power as a receiving end voltage as a function of real power received by the load. And how actually this PR and VR are affected by the reactive power injection. That is, at the load point, suppose we inject reactive power, then how this reactive power is going to affect actually the variation of VR with variation of PR with variation of VR. That is, as you increase the value of PR, the voltage will vary. In fact, these graphs which were plotted earlier, they were plotted actually for considering the cos phi as 0.95 and the value of theta is such that tan theta is equal to 10, right. The theta is the phase angle of the source impedance or the line impedance, right, and we know that the line impedance has a large phase angle, therefore tan theta is 10. Now, we show another very important actually form of characteristics, where we plot the variation of receiving end voltage VR as a function of PR by PR max. That is, earlier the voltage, power and current were plotted as a function of load impedance. Now, we plot here the normalized receiving end power, that is PR by PR max. This quantity is PR divided by PR max, that is the maximum power, it is normalized power. On this axis we put the normalized voltage VR by VR ES, VR divided by ES is normalized receiving end voltage. Now, this graph is plotted for different power factors. Now, here if you can see here, then this graph or this curve represents the variation of PR and VR, the relationship between PR and VR for power factor equal to 0.9 lagging. And I think let me make it more dark here. These graphs can be shown in the more one typical graph is plotted here for power factor equal to 0.9 lagging. The graph looks like this. This is the graph. So, only one graph like this. That is, what we see here is that as the receiving end power increases, the receiving end voltage decreases, and it comes to a point where the receiving end power increases and the receiving voltage also drops. But if you try to, you can say, increase the power beyond this point, you will find actually you will not be in a position to increase the power, and the power will decrease and the voltage will decrease. That is actually from this point to this point, it becomes the unstable operating point. You cannot operate on this point. Similarly, for different power factor, this graph represents for 0.95 lagging, this graph represents the relationship between PR and VR for unity power factor. Then the graphs are plotted for leading power factor condition 0.95 and 9 lagging. Therefore, if you join these critical points, which is the maximum power which can be transmitted without losing voltage, without occurring or without coming to the voltage instability problem, right. Now, these points are, when we join together, these are given the name of locus of critical points. right. Therefore, for a simple power system looking at one particular bus, that is, if you take a system and represent by equivalent Thevenin network, then we can always plot this type of graphs, which are normally called actually the nose curves. They look like nose, they are nose curves, right. And especially here, this is the critical point, right. Therefore, the operating point will always be away from this critical point. Now, suppose you have now a large interconnected system, then for this large interconnected system, how to draw similar type of graphs. Now, to illustrate this phenomena, what is done is that one has to perform load flow study for each and every operating condition. Therefore, to illustrate actually for how we plot this type of graphs for a multi machine system or for an interconnected network. A typical network considered is a 39 bus 9 generator with one synchronous condenser network. This is a very of course, the network is not very clearly visible, but this network is given in both the reference books. This is discussed actually in the by Prabha Kundur in chapter 14, taking this network, it is 39 bus, 9 generator and one synchronous condenser. This network has also been discussed in this book on power system stability by Taylor, right. Now, here to illustrate this voltage stability phenomena, what is considered is that a portion of the network is examined. Now, a portion of the network which is examined is, I will just show you here. It is a big network having actually 39 buses and some generators there are, they are all generators, and this is the synchronous condenser which is shown here, right. Now, in this network, this bus is the farthest bus and denoted as bus number 530 here in this network. Therefore, to plot this the power output versus the voltage characteristic, what is done is that this is considered as one particular area in which the load is increased at all the load points slowly. That is, you increase in small steps the loads at all the load points which are given here, where at all the buses which are enclosed in this area, right, and all the loads are increased in small steps. Then for each of the loading condition, a load flow program is run, right, and for running the load flow program, what is done is that whatsoever is the increase in the load here, the output from the generators are also increased in proportion to their capacity, because we know that real power balance is to be maintained. If you increase the load, the generator output has also to be increased, right. Therefore, to analyze this system, the voltage at the bus number 530 is plotted for different loading conditions which are considered in this area. This is the area which is enclosed, right. And for this each of the loading condition, a load flow is run, and when you run the load flow, you will get the voltage at this bus 530, right. Now, this is the graph which is plotted for this particular network. On this axis of this graph, we are marking the total active power in megawatt in area 1. That is, I have already specified that this portion of the power system is considered as area 1, right. Therefore, in this area, the total total active power is varied, right, and for each active power loading, right, the load flow is carried out. But when you have varied the active power, the reactive power are also increased in the same ratio. So, that the power factor is maintained at the same level, that is at each bus the same power factor is maintained. Now, the graph which is plotted is here. You can see that this is one point on the graph when the loading is something like about 80 plus megawatt. As you increase the load from 80 megawatt to 200 megawatt, right, what we see here is that voltage at this bus, the bus which is considered is the bus number 530, which is expressed in per unit, this voltage drops. It comes to point B, it comes to point C. At point C, that is if the total load in area 1 comes to the level of something like 190 megawatt, you will find actually that the load flow will not converge. It means actually we have reached the critical operating condition, and beyond that if you try to can say load the system will become unstable, voltage collapse will take place. So, another very important characteristic which can be used to understand the voltage stability phenomena is the relationship between the voltage and the reactive power injected at a particular bus. That gives actually the suppose I inject a reactive power, right, then how the voltage at that bus increases, bus varies, it may increase or decrease, right. Therefore, for the same system which we have studied, there is 39 bus 10 generator system. Here we consider 10 machine system, because 9 generators and 1 synchronous condenser, that becomes the 10 machine system. For this system, one can plot the graphs relating the reactive power Q I injected at a particular bus versus the voltage at that bus. Now, these graphs are generated for the different buses. For example, bus number 530, which is the most critical bus in that area 1 of the 39 bus system. On this axis we are marking the bus voltage in per unit, and on this axis we are marking the reactive power Q I in MVR, right. Now, the voltage at this bus 530 is concerned, you can see here actually that the variation of this voltage with the variation of reactive power which is injected is practically quite constant here. That is, for different voltages you can see that this voltage is practically constant, it is something like this. Now, from this point onwards what happens is that the voltage start increasing, right. Therefore, you can see that for something like this 0.6 and beyond, if you increase the injected reactive power, the voltage increases. It means if you take the ratio of voltage to delta V to delta Q, then this is a positive quantity. The voltage increases where the reactive power also increases. Now, if you see this one typical bus number 200 in the same area, then the variation is very difficult, very sharp. You can easily see that this is the type of variation. Like this. Now, in this case, at the point there is a lowest point here on this graph. That is, if you are on this side of the graph, just if you are on this side of the graph, what we see here is that as the reactive power injected increases, you see here actually the reactive power we consider as a reactive power injected is considered as a positive and reactive power absorbed is considered as a negative, right. Therefore, when you can easily see that here when you increase the reactive power, particularly you can just see here, then the voltage decreases because the graph is like this. That is, with the increase in the reactive power injected, the voltage is dropped. Therefore, this part of the graph represents actually the unstable condition. Now, from this lowest point onwards, what we see that when you increase the reactive power which is injected at that particular bus, the voltage also increases. As a simple rule, actually the rule is that at a particular bus when you inject the reactive power, right, the voltage when it increases, that shows the stable condition. If the voltage decreases, that shows that we are moving towards the voltage collapse situation. The similar graphs are plotted actually for different loading conditions. This is the graph which is plotted for the loading condition which is shown here A, because there are 3 different loading conditions which are identified in area 1, and for this loading condition the graphs are plotted for different buses in area 1, and these are the show the variation. It means you can easily see that except at most of the buses there exists actually a region where the voltage increases with the increase in reactive power injection. Now, these graphs are plotted for the second operating point which is shown here. This is the operating point, the heavy loading condition. For this loading condition, you consider that loading condition and see the sensitivity of the voltage at a particular bus by injecting the reactive power, right. These graphs show the variation of the voltage, bus voltages of the buses 200, 160, 510, 530, that different buses in the same area, right. You can easily see here actually that yes, we have some minimum point, and from the lowest point there exists a region where the voltage is going to increase with the increase in the injected power. Now, these are the graphs which are plotted, you can see here, they are the graphs which are plotted for the third operating condition, that is the critical point. At this critical point you can easily see here actually that, can you see actually that there is a large region or that the minimum point is occurring at these points. You can see that this is the minimum point here, this is the minimum point here, while earlier the minimum points were occurring on this side. See this, suppose you see that this minimum points are below 0.6. Similarly, you can see the minimum point here again on this side, but if you see the minimum point here, they are occurring somewhere actually around 0.6. This minimum point is somewhere here. Therefore, at this critical point you will find actually that the voltage sensitivity or actually the relationship between the Qi and the bus voltage, there is a large portion where the system will become unstable. There is a certain portion actually, if we are operating beyond this particular point, then yes, you will be in a position to operate stably. But if you are operating below that particular voltage condition, then you will find actually the voltage will decrease when you are injecting the reactive power. Now, here I will actually like to mention one very important point. What is the effect of on-load tap changer on the voltage stability phenomena? Now, suppose we consider a system, a very simple system, right. I am drawing only the one line diagram. Now, if this system is supplying a load, let us say it is a constant impedance load, right, and this is supplied through a transformer. Here is a transformer connected. Here is a transformer which is connected. Okay. Let me show this transformer here. And the load is connected here. At this point, we are connecting the load, and we are assuming here that the load is a constant impedance load. This transformer is provided with under load tap changer, right. Now, when you increase the load here, let us say that increasing the load impedance, so not load impedance, you are actually reducing the load impedance to increase the power, or otherwise you can say that we are increasing the load admittance. Now, if the voltage drops here, the action of the ULTC is, what is the action of this ULTC? It will try to maintain the voltage at this point. And how does it maintain the voltage? By changing the transformation ratio. Suppose the transformation ratio is determined by this quantity N1 by N2. N is the primary turns, N2 the secondary turns. Now, to boost the voltage on the secondary of this transformer, the ULTC will work so as to reduce N1. So, if you reduce N1, then what will happen is that voltage at the other end will increase. Applied voltage is same, right, so that it is stepping down by a different ratio. Suppose you take a ratio, let us say the N1 is 1000 and N2 is 100, right. Then input voltage is stepped down by a factor of 10. Now, suppose instead of 1000 I make it say 950, therefore, it will be stepped down by a factor of 9.5. It means this is, through this effect this transformer is trying to maintain the voltage. But now, this load impedance, when it is reflected to primary side, that is the load impedance when it is reflected to primary side, what happens? The ZLD prime will be equal to N1 upon N2 square into ZLD. That is, when you refer actually the secondary impedance to the primary side, this is the impedance which is referred. Therefore, here what has happened is that ZLD decreased. So, that power consumed was, to increase the power, ZLD was decreased. But now what happens that system will see that the ZLD is further decreased, because N1 has been decreased. Now, when therefore, the impedance which is seen by the system is now decreasing. When impedance decreases, the voltage will further decrease. When voltage further decreases, ULTC will again try to increase the voltage by reducing this ratio. When it reduces this ratio, again this ZLD is going to be decreased. Therefore, this becomes a cumulative phenomena, and therefore, in this particular situation where you have a constant impedance load, the operation of under load tap changer is adversely affecting the voltage stability. Normally, one should always think actually that yes, the ULTC should be in a position to stabilize the voltage, right. But here in this particular case, incidentally, when they are operating on the other part of the curve, that is, we have the curve where the when you decrease this impedance, the power is increasing, but after certain maximum value, the power decreases and voltage decreases. Power increases, but voltage decreases, right. If it is a constant impedance load and you do not have this ULTC, you will operate at a stable point. But the moment you have provided ULTC which is trying to boost the voltage at the load point, you will find that in a sequence that ULTC tries to increase the voltage, the impedance in further decreases and so on. Is it understood like that? Therefore, ULTC's effect or the under load type changer operation, it plays very significant role actually in the stability of the power system. Now, let me sum up what we have discussed today. I have introduced the basic concepts of voltage stability, and I have also introduced that what is all what we are going to discuss in the voltage stability problem. Then I have given the basic characteristic of a transmission line. We have plotted the variation of voltage, current and power as a function of variation in load impedance. Then we have generated the nose curves for a multi-machine system, also a technique how to generate the nose curves for the multi-machine system. And I also introduced the basic concept of the voltage reactive power sensitivity.